Last time we were talking about how to generate fuzzy sets using GIS software, and we had actually we had one example, high elevation, and you remember we have this data set that you also can download, and we have last time built a project in QGIS and one in ArcGIS Pro. Once again, for those who don't have ArcGIS Pro and want to use ArcMap, you just create a new map in ArcMap and you enter the data, and it's basically the same. So in this particular example, we had high elevation, which is defined by a sinusoidal membership function, and in such a way that an elevation up to 1,700 meters, the membership to high elevation is 0. Between 1,700 and 2,000 meters, it increases according to the sinusoidal membership function, and above 2,000 meters, the membership is 1. So we can do such calculations using the raster calculator. The raster calculator is a tool that's available in ArcGIS and also in QGIS. So what I'm going to do here is I'm going to show you how that can be done in QGIS and in ArcGIS. For that purpose, I will first go to, I have prepared one text file, this one, where I have the code that we will need for the raster calculator. Let me just perhaps make the font a little bit bigger so that you can see it better. Okay. I will make that file also available to you. For the ArcGIS raster calculator, we use a, for those of you who are familiar with the map algebra and the raster calculator in ArcGIS or ArcMap, there are conditional statements. It's like an if then else statement. The conditional statement basically works con, defining a condition, then what happens when the condition is true, and then what happens when the condition is not true. So for ArcGIS, we would say if the condition elevation less than 1,700, then the value of the membership is 0. Otherwise, if the elevation is less than 2,000, the membership is computed according to our sinusoidal membership function, which is 0.5 times 1 minus cosine of pi times the membership function, the elevation minus 1,700 divided by 300. And in all other cases, it is 1, meaning when the elevation is above 2,000 meters. So what I'm doing here is I just copy that statement. I go to my ArcGIS, in my case, ArcGIS Pro project, where we see we have our data here. I just click away the other features, and this is the elevation model. Then we have in the under analysis or in ArcMap, you would go to the toolbox. In the toolbox, in the spatial analyst tools, we have map algebra and raster calculator, where we have the raster calculator, and I'm just pasting my code here into the raster calculator, and I say, okay, the output raster should be, or the output fuzzy set actually should be high elevation. So, and when I run this statement, okay, it is done. I'm just swapping here the gray values. So 0 is white and 1 is black, and everything in between are membership values between 0 and 1. So this would be our fuzzy set for high elevation computed in the raster calculator of ArcGIS Pro. So what you can see here, if I just for a moment click it away, and when we look at our elevation, let's look at this part. What we see here, we have here the city of Boulder. This is a rather low elevation here. As I mentioned last time, the city of Boulder is at an elevation of 1,600 meters. And to the west, we have the Rocky Mountains that reach heights of up to more than 2,500 meters. So if we have this high elevation, you can see that towards the west, we have high membership values, in many cases even a membership value of 1, because the elevation is above 2,000. So this gives us the result in ArcGIS, and it works in the same way in ArcMap. If I switch now to QGIS, also in QGIS, we can use a conditional statement. In QGIS, it would be the if statement that works in the same way as the conditional statement in ArcGIS. So if a condition is true, then, if, for example, if this condition is true, then do that. Otherwise, do this. So it's exactly the same thing. More or less, we copy our statement and we go to our QGIS where we have the elevation here. So we have our elevation raster here, and when you look into the QGIS processing toolbox, we have raster analysis, and in the raster analysis, we have the raster calculator. Our elevation model here has the name elevation at 1. This is a convention that QGIS uses to name. Actually, this is the band 1 of the DEM raster. If you would have more bands in a raster, this number here would indicate which raster band you are using. And we paste our statement in here. And then we just have to do a little bit more here. We have to give a reference layer telling QGIS what would be the extent and the cell size and the coordinate reference system of our result. So what I'm doing here, I use the elevation model as the reference layer, and I create an output file. In this particular case, I do not write it to disk. I use a temporary file here as output, because later on in our example, we will not use that. So I use a temporary file, and I can run this raster calculator, which gives me a result. Again, you can see here my result. What I'm doing here again is swapping from black to white to black, so that we have 1 where the membership is highest and 0 where the membership is not given. So again, you can see here we have generated this fuzzy set that corresponds to high elevation. And all raster values in that fuzzy set, in that raster, all values are between 1 and 0. So, but there is one more thing before we go into our concrete example. Last time we had, I gave you an exercise. We should look at that exercise also. This exercise was given in such a way that we have membership functions for flat and steep slope and for favorable aspect. And then we have membership functions for the risk, low, moderate, and high risk, and a set of 4 rules. And you should implement a fuzzy reasoning model using these membership functions and that rules, and then do it according to Mamdani's direct method. So the result would look like this. Here you see the membership function for flat and steep slope. Here for favorable and unfavorable aspect. Here that would be the membership functions for low, moderate, and high risk. And then you could do it exactly according to what I have given you as another example. You remember an example with the cars, with the distance and the speed of cars. So you just could use the old one as a template and implement it here, and then you have your results where, for example, you could say if the slope is 15 and the aspect is 0, aspect 0 means north, then the value of the risk value would be 2.78. On the other hand, if you take a steeper slope, then the risk value increases. If you take a favorable aspect, like this, let's say we take south, then the risk value goes down to 2.5 and so on. So I have seen that basically everybody of you has submitted this exercise, and I have just taken a brief look at it, and I think you basically got it right. Now let's move back to our class. As I said, today we are going to discuss a case study doing a fuzzy site analysis. And if you remember, let me just jump back right to the beginning of our course. There we had an example where we said we are looking for all those areas with a flat slope, a favorable aspect, moderate elevation, close to a lake, not near a major road, and not in a military installation. And we said, okay, if we do it in the traditional way, that we use GIS, we have to set clear boundaries. For example, flat slope is everything less than 10 degrees, or elevation is moderate when it's between 1,500 and 2,000. So these are strict clear boundaries, and then we do our analysis in the GIS. In this particular case, I think I did it in ArcGIS Pro with the same data that we are using, and then you see on the right-hand side, that would be the result. Now, what we are doing now is we are doing the same example, but we will be using a fuzzy approach. Okay, let me go back to our chapter here. So we do a fuzzy site analysis with our boulder data set, and we are looking for all those areas with flat slope, favorable aspect, moderate elevation, close to a water body, not near a major road, and not located in a park or military installation. So all those conditions, except the park and the military installation, all those conditions are fuzzy conditions. Only located in a park or military installation is not fuzzy because there is no fuzziness in that condition. So how are we going to do that? We have to create fuzzy sets for all that criteria, and we basically have our data. If we just go to QGIS, click this away, our high elevation, I will remove this layer from my map. Okay, so we have basically we have all the data. We have the major roads. As you can see here, these are the major roads. We have okay, the rivers I don't need to show because we are not using the rivers as a condition. But we have the parks here, a large park, military reservation, a small park, and we have the lakes. And for the lakes or for the water bodies, we will only use lake or pond or reservoir. Of course, sewage disposal pond or covered reservoir doesn't make much sense for us. And of course, we have the elevation model. So we have all our basic data to perform power analysis. Okay, we are going to do that now step by step. We are doing it step by step, starting with flat slope. Now, flat slope we define as a fuzzy set using a membership function that has the two parameters. We are using a linear membership function, saying that at the slope of 0, the membership to flat slope is definitely 1. Then with increasing slope, the membership values are decreasing and become 0 at 20 degree slope. So it's a linear membership function that has the crossover point at 10. That is the boundary that we have chosen for flat slope in our traditional GIS analysis, where we said, okay, everything with a slope less than 10 is okay. If it's more than 10, it's not okay. And now here we define a fuzzy set that has the parameters 0 and 20, and we compute fuzzy slope from there. Now, in the slides, you always see how we are going to do that and what the result should look like. And we are going to do that now step by step in our GIS software. Now, let me jump back to our QGIS. We have here our map, and we need to compute fuzzy slope. So we have the elevation model. First, we have to compute the slope from our elevation model. So in the raster terrain analysis, we have the slope. As elevation layer, we use our elevation model, and we store our result. No, actually the slope I will not store. I keep it as a temporary file because I'm not going to use this. I'm going to use the slope only as an intermediate result for our fuzzy, for our flat slope. So this would be the thing to compute the slope. So let's run it. Okay. Now we have a slope here. As you can see, here we have the slope, and from that we can now compute our flat slope fuzzy set. And in doing that, we use the functions that we have available in the raster analysis. You can see here we have a fuzzy raster, a linear membership. So we are going to use the linear membership function. As input raster, we use the slope. It has only one band, so this is so we don't need to do anything here. And here we have to enter the parameters for fuzzy for our fuzzy set. Now we have a low bound and we have a high bound. Normally, if the low bound is less than the high bound, we have an increasing membership function. But this is not what we need here. In our case, we need a decreasing membership function, meaning for higher input values, we should get lower membership values, and we can achieve that by swapping the bounds, meaning that at the lower bound we have to enter our 20, and at the lower bound we have to enter our 0. In this way, we achieve a decreasing membership function, and this one we are going to save to a file, and I will save it to a file that I call fslope, or fuzzy, for fslope for fuzzy slope. This is all what we have to do here, and we can now run our fuzzy slope, which gives us here, I click away the slope. This is our fuzzy slope now, meaning flat slope. And as you can see, the gray values I have to swap because I want black 1 and white to be 0. Now this is our fuzzy slope now, and of course, as expected, as you know from the topography of that area here in the east, it's rather flat, and to the west we have the Rocky Mountains. Of course, there we have steeper slopes. So here to the east we have high membership values to flat slope, and towards the west we have lower membership values to flat slope, and many areas are white, meaning the membership is 0 because the slopes are too steep in that area. Now, this is now our flat slope. We basically have already computed our first criterion. Our first criterion, flat slope. Then we have to go to the next one, which is favorable aspect. So favorable aspect we define in such a way that we say, and you know, aspect is calculated or computed as degrees from north. So north is 0. Then east is 90, south is 180, west is 270, and 360, or 0 is again north. So what we say here is a favorable aspect is starting at east. So from north to east is definitely not favorable, so the membership values are 0. Then the membership from 90 increases to 180, meaning from east to south, and the membership becomes 1 at due south. Then it decreases again till west, which is 270 degrees, and from there on it stays 0 again. So this will be our parameters for a membership function. And in this case, it will be a triangular membership function with a value of 1 at 180, which is due south. And we will create such a triangular membership function, again, using our fuzzy tools that we have in QGIS. So you see it here. In our particular case, in QGIS, we do not have explicitly a tool for triangular or trapezoidal linear membership functions. So we have to generate it by ourselves by first creating or generating the ascending part of a linear membership function. The ascending part is the part between 90 and 180, where the membership values increase. Till 90 they are 0, and at 180 they are 1. And then we have to generate a second set for the descending part, meaning from 180 to 270. At 180 it's 1, and at 270 it becomes 0. you can see here again the descending part we do by giving the higher value for the low bound and the smaller value for the high bound. In this way, we achieve a descending membership function. So now we have two membership functions, and we have to compute the intersection of these two so that we can get our triangular, in this case, yes, our triangular membership function. And we do that with the minimum operator. You remember an intersection of two fuzzy sets can be computed in the easiest way by using the minimum operator. Let me perhaps illustrate why I use this. So I need another blank screen. And I need a pen. So what I was doing is I said, okay, I'm creating a first. Sorry, that should be straight lines. Yeah. So I'm doing the following. This is 90. This is 180. I'm drawing with the mouse, so that's why it's a little bit awkward. So we have here, this is the ascending part. And then I create a descending part where I say, where's my pen? I create a descending part where I say, okay, till 180, then it decreases, and from there it stays. This is 270. And now you can see to achieve this triangular function, we intersect both of them, and then we only get, by intersecting both of them, we get basically this area under here. And this is exactly what we want to have. So now let's go back to our GIS. So we have to first create the aspect, because we don't have that yet. Of course, the aspect can be computed with the terrain analysis tool. So from the elevation model, we compute the aspect. We don't need any further parameters here. So we run our aspect, and that would be the aspect. And now from that, we can compute our favorable aspect. And we do that again with our membership functions, as we have, as I just have explained on the slide. So we use a linear membership function. We take the aspect as an input. Now we compute the ascending part, which means from 90 to 180. We save it as a temporary layer. Okay, and then we compute the descending part with 270 and 180. Again, as a temporary layer. And now we have to compute the intersection of both of them. And we are doing that with the raster calculator. We are doing that with the raster calculator. The raster calculator has several operands here, and one is the minimum operator. So we use the minimum operator. of our two falsified rasters, this one and the other one. And then we again have to give a reference layer so that the result has the proper extent and the proper coordinate system and the proper raster cell size. So we use the elevation model as the reference. And for the output, we save it to a file and we call it fuzzy aspect or F aspect. So it should appear here in a second, and then we can run it. And now we should have a fuzzy aspect where again I swap the color ramp from 0 to 1, 0 white and 1 black. And this is then our fuzzy aspect. So the darker the gray values here, the more favorable the aspect is in our particular case here for our topography that we have here. So I can remove these layers here, or intermediate layers that I don't need anymore. And we keep our fuzzy aspect and fuzzy slope. I move the slope up here. So we have now already computed 2 conditions. That was the fuzzy aspect. Our third condition is moderate elevation. We define moderate elevation in such a way that we say we are using a trapezoidal membership function, so that up to 1,000 meter elevation, it's definitely not moderate. Then it increases to 1,700 meters, where it becomes 1. It stays 1 till 1,800 meters. So the range between 1,700 and 1,800 has membership values of 1. There it's definitely moderate. And then it decreases again when the elevation goes beyond 1,800 to 2,500. And from 2,500 on, it definitely is not moderate anymore and it stays 0. So we can calculate that fuzzy set for moderate elevation from our elevation model using in this case, we use a trapezoidal membership function, not a triangular as we did for the aspect. We use here a trapezoidal function, and the approach is exactly the same as it was with our fuzzy aspect. We need to calculate the ascending part using a linear membership function with the parameters 1,000 and 1,700, as you can see here on that slide. The ascending part, lower bound 1,000, higher bound 1,700. Then we compute the descending part, where we have to use the higher value for the low bound and the smaller value for the high bound, so 2,500 and 1,800. Once we have these 2 fuzzy sets, again, we have to compute their intersection by using the minimum operator in our case, which will give us this result for moderate elevation, where you then can see again, of course, towards the west, the elevation is more moderate because it is in a range that is good for our elevation, and the higher it gets, the less moderate the elevation becomes. So now let's again jump back to our GIS and compute the moderate elevation. So first we need, as I said, we need the linear membership function for, we take the elevation model as an input. We have the lower bound of 1000. What did I say? I forgot my parameter. I have to check it. Oh, yes, it was 1000 and 1700. Again, we will generate a temporary file for that, so we can run that. Then we calculate the decreasing part, which was 2500 and 1800 as parameters. So that gives us then the descending part. And what we have to do now is we have to, here we have those falsified rasters. And now we have to use the raster calculator to compute the minimum or the intersection of these two, raster 1 and raster 2. Again, we have to set a reference layer. We use the elevation model as a reference layer for the extent and the cell size and the coordinate system. And we store it to a file, which we call F elevation for fuzzy elevation. So it will take a second. Okay, now it's here and we can run it. That should do it. And now we have our elevation. Again, I'm going to swap the color. And I will move it up here. So this is now our fuzzy elevation, or in other words, our moderate elevation that we have defined here. So once again, we can take a look at our 3 criteria that we already have computed. Let me first take away these layers that we don't need anymore, or intermediate layers. Okay, so we have the fuzzy slope, we have the fuzzy aspect, or in other words, I should rather say we have the flat slope, we have the favorable aspect, and we have the moderate elevation as 3 fuzzy sets already in our analysis. And now we are talking about the next criterion, which is close to a water body. Water bodies in our particular case are lakes or ponds and reservoirs. And we will first have to extract those water bodies from our layer. And we can do that by a tool which is called extract by expression. When I gave you the data for this example, the boulder data, I also gave you the information in which attribute you can find the attribute values. In our particular case, for the water bodies, it's the attribute entity depth, where you can find the values that we are looking for. And the expression that we can use is an expression here that is used in QGIS. So we use the name of our attribute entity def, and then we use the is operator, and then we use the values that we are looking for. So in our particular case, entity def is lake or pond, or entity def is reservoir. So both are the ones that we are interested in. What happens after we do that? We get a vector layer that only contains those features that are lake or pond or reservoir. After that, we have to rasterize that layer. So because this is a vector layer, so we have, after that, we have to create a raster from that layer, and we are doing that with the rasterize tool, vector to raster, that you can find in the tools of QGIS. On the left-hand side, I have shown here where you can find it. It's in the GDAL under vector conversion, rasterize vector to raster. And we will have to use our vector layer and then give some parameters. For example, what we give here, this is the parameter, it's called the burn, or the value to burn, meaning where we have now our vector feature, the raster should have a value of 1. Then we use the georeferenced units from our vector layer and not pixels. The size of the pixel size of our raster, or the raster grid size, is 10 by 10. I did not mention that, I think, before, but the elevation raster of this boulder data set has a resolution of 10 by 10 meters. So all our rasters that we use, we will use a 10 by 10 meter raster resolution, so that all our raster layers fit together. Then we give an extent. For the extent, we use our elevation model, and for the rest, we don't need much more. I just use as a data type, I use float 32. And then we have, after that, we have a raster that contains only ones where we had our vector features. And now we have to compute from that raster a distance raster, giving us the distance in map units from every raster cell that is 1. And this can be done with the proximity tool, proximity raster distance tool, that you find again here in the GDAL library under proximity raster distance, where we will enter our rasterized layer. We will use as distance units not pixels, but the georeferenced coordinates. So we want to have the distance values in meters. The other parameters we don't need. As output data type, we use float 32, and we will store that as a temporary map. The result then will look like this. So wherever we had water bodies, I use grayscales here to indicate the distance from the water bodies. So every raster cell in this map here contains the distance in map units, in meters, from the nearest water body. Once we have done that, we have now our distance raster, and now we can compute our fuzzy set close to a water body. And we are using again, we will, for simplicity, we are using a linear membership function with the parameters 2000 and 0, meaning when we, for example, were doing that analysis with the traditional approach, we said everything within 1000 meters from a water body is okay. Everything outside 1000 meters is not okay. So I choose here the parameter 2000 that gives me a crossover point at 1000 where we have placed our boundary, our class boundary in the conventional approach. And since I want a close to water body, meaning the closer to the water body, the higher the membership degree, the further away from the water, the lower the membership degree. I have to use a descending part of our linear membership function, again, meaning I have to swap the parameters. I have to use the higher value for the low bound, and I have to use the smaller value for the high bound. And then we get this result where we see again the darker, the closer to a water body, the more white or gray and white, the further away from a water body. And now let's go and see how we are going to do that. So first of all, we said we have to extract the water bodies using the extract by expression. So I make it easy for myself. I just copy this text here. Then I go to our map. Let me click this away. Then I go to, where is it? Oh, I lost it. It's in the vector selection toolbox. Vector selection here, extract by expression. We are using as input layer the lakes. These are our water bodies. I can paste the expression here. And we are creating a temporary layer here. That should do it. Okay. So we have now a temporary layer with our matching figures. If I click everything away here, the only thing that remains are our matching water bodies. Now, I have my water bodies as a vector layer. What I have to do next is I have to rasterize it. As we said, we use the vector to raster, rasterizing under vector conversion. Here the GDAL, vector conversion, rasterize vector to raster. Okay, my input layer is our matching features that we just computed. The fixed burn-in value should be 1. Then our output raster size units should not be pixels, but georeferenced units. The raster resolution is 10 by 10. The output extent, we use the elevation model as the extent. Then what else do we need? We need, okay, we use float 32 as a data type, and I think we are done. Just let me verify once more. The georeferenced units, yes, burn-in value 1. Okay, you see something happened. That should also be 10. Raster resolution. Yeah, now I think we are good. we can now run it. So this is now our rasterized result. And the next step is to compute the distance raster. And again, as I said, we use here the tool proximity raster distance from the GDAL library. Oh, where is it? Again, I lost it. It's in the what? In the raster analysis tools. Okay. It's in the raster analysis tools, proximity, here it is. Okay, we use our rasterized layer as input. Then again, we use georeferenced coordinates. There we don't set any values for these parameters. I think we are done. Let me just double check. Yes, should be okay. Georeference coordinates float 32. That's our distance raster. Yes, I don't think any more parameters are needed. Nope. Okay. So this is now the proximity map. And you can see here, if I flip again the color scale, you can see here the distances are between 0 and 4,000 meters. And now from that, we can generate our fuzzy set close to a water body. And we use our linear membership function, where we take as input our proximity map. We set 2000 for the low bound and 0 for the, 0 for the high bound. And we save it to a file and call it F water, so fuzzy water. Fine, that should be fine now, and we can run it, giving us this result. Again, I'm inverting our color scale. And this is our fuzzy should be our fuzzy close to a water body. If I just for a moment take the water bodies. So we have here water bodies, and you see the closer to the water body, the darker. Okay, so let me remove the layers that we don't need. And also this one. Okay, so now what we have is we have now also the close to a water body condition. The next condition that we have to look at is not near a major road. Not near a major road. We have defined the major roads in our map. These are the US 36. The SR, US stands for US highway, and SR for state road, the SR 93, the SR 7, and the SR 119. So these are our major roads. Again, we have to extract these roads from our road layer. Then we have to rasterize it. Then we have to compute the distance raster, and then we can compute our fuzzy set not near a major road. And for not near a major road, in our traditional analysis approach, we said, okay, everything that is within a buffer of 300 meters from a major road is not okay. So it must be at least 300 meters away. Again, that was our crisp boundary. So in our case for our fuzzy set, we use 600 as a parameter. Then we have the crossover point at 300. And in this case, it's an ascending membership function, meaning the bigger the distance from the road, the greater is also the membership value. So the low bound is our 0, and the high bound will be our 600. Okay, now going back to our GIS, we first need to extract the we need to extract our it's in the GDL library. Where was it? I always lose that stuff. It's the vector selection extract by expression. Vector selection, extract by expression. Take the roads as input. Okay, I have to copy my expression here. This is the expression. Then this is basically all we need to do. Get the temporary layer. These are the matching features. Now, what we have to do is we have to rasterize it. Rasterize a per-mean value of 1. Georeferenced units, the raster resolution will be 10 by 10. That should do it. Let's check it again. Per-mean value 1, georeferenced units, raster resolution 10 by 10. Output type float 32. That should be the same as we had here. Fine. Let's run it. This is done. And now we need to compute the distance raster. Raster analysis proximity. proximity raster. So our input is the rasterized, then the georeferenced coordinates. Here we don't set these parameters. Float 32, and the output is also our temporary map, so that should be fine. Double check. Yes. Okay, still georeference coordinates fine. So this is now our proximity map. And again, if I want to see that. So the further away from a major road, the higher the value. So the maximum is about 8,000 meters. And now we can compute our fuzzy set. We take the linear membership function. We take as input our proximity map. And we said we have the parameters of 0 and 600. 0 and 600, and we save our result to a file, which I call froad or fuzzy road. Okay, let's check again. Proximity map, 0, 600, froad, fine, we can run it. This is done. Okay, I just click this away. And then take care of the color. So, what happened now? Something is strange. Just was there for a moment. Okay, whenever you do something live in class with GIS, something might go wrong. Okay, what I'm going to do is I do it again. Don't know exactly why it doesn't show. I remove this layer and I do it again. Fuzzy linear membership function. Proximity map. Okay. Okay. I can see it now. I hope it doesn't flip again. It doesn't. Okay, I don't now change the color scale. I don't know why it went wrong last time. Here now we have the closer to the road, the higher, the darker the value, the further away, the whiter the value. So actually I want it the other way around, but it's just a graphic thing. So let's leave it for the moment. And let's move on to the other criterion. So let me remove these layers that we don't need now. Okay, so we have now already the flat slope, favorable aspect, moderate elevation, close to a water body, not near a major road. Fine. There is only one more criterion that we had, and that was no park or military installation. So in fact, this is not a fuzzy thing. So what I'm going to do here is I extract all the parks and military installations, again with the extract by expression tool. And what we have is we have a large park as values. We have a large park, we have small park, and we have military reservation. So I will extract them. Then I will rasterize them. And then I will reclassify this raster by assigning a 0 everywhere we have a park or military installation and a 1 otherwise. So we have a binary raster as a result, where we have a 0, where there is an exclusion area, meaning a park or military installation, and a 1 everywhere else. And I will do that again then with the raster calculator using an if statement. So it will be if our raster is equal 1, then it should be 0, otherwise it should be 1. Okay, and let's go to that. First I have to extract the features, extract by expression. Again. Make the selection now. Extract by expression, take as input the parks. Here is our expression. Create a temporary layer, that's fine. So we have a temporary layer of all our parks. The next thing is we have to rasterize it. Vector to raster. So we take our matching features. We use a value of 1. We use georeferenced units. We create a raster of 10, so 10 by 10. As an extent, we use the same extent as the elevation model. And that should do it. Again, 10 by 10, yes. So we run it. This is now our rasterized features. And now we are going to change the values. We're going to reclassify it using the raster calculator. So we are using if our rasterized is equal 1, make it 0, otherwise 1. Then as a reference layer, we use the elevation model. the cell size, and should all be taken from our reference layer. And the output should then be a layer which I call no parks. Okay, that should do it. Something is not quite okay, I guess. Oh, interesting. It's not quite okay. Okay, let's remove it. Let's do it again. The rasterized layer, yes. Let's use the raster calculator from here and see what happens. Rasterized. Okay, that's now. If rasterized equal 1, 0, otherwise 1. Let's see if this works. Okay. Okay, something went wrong here. I'm not quite sure now what went wrong, but for the sake of the time, let's just skip that for a moment and move on to what we would do next. Next, we would calculate the final result, which would be the intersection of all our fuzzy layers that we have generated. And what we do is we use the multiplication operator here for the intersection, meaning we have to multiply all our fuzzy sets. And that gives us a result. Wherever we would have a 0, of course, that result would be 0, meaning it's not in our final result. But all the other values that are between 0 and 1 will have some values, some gray values, as I would say, and that is then our final result. So let's look at this and just let's leave for the moment the parks out and just use the other criteria. So jumping back here to the raster calculator, and let's see, what we need to do is we need to multiply all of them. Let's say starting with fuzzy aspect times fuzzy elevation times fuzzy road times fuzzy slope times fuzzy water. I leave the parks now out because I'm not sure what which result we had here. So let's leave it out for a moment. As a reference layer, we select also we select the elevation model. And for the output, we store it to the file, which I call final. And then we run it and see what we have. So this would be our final result. And please note that at this time we did not exclude the parks because something went wrong in my calculation. I would have to check what went wrong. But you can, let's say, you can recreate it by following the instructions on the slides that you have, and I hope it will not go wrong in your case, because there are some areas where there are lakes that should be excluded. Not only the lakes, but the parks should be excluded. The lakes will be in also if we are looking for, assuming we are looking for an area where we want to build something, then of course the lakes would not make much sense, but they're still there. Here you can see there is a lake, but all the parks are up there. In this corner there was a military installation, and there were other parks here. You can clearly see also the major roads here, they are white, meaning the membership values are 0, because our criterion was not near a major road, but it should be near a lake. And here we have a lake. I don't know, I can see if I can move a lake up here. Let's move the lakes up, display the lakes. So you can see here the lakes, and near the lakes you have high membership values, and when I display the roads, just here you can see the major roads, and you can clearly see that there are the values 0 near the major roads, and the further away you get, the higher the values become. So what we have here is basically our final result. When you look at the slide here, you will see that on the final result of where we have excluded the parks, we have here a white area, because in this northeast corner, there is a military installation that would be excluded, of course, and there are other parks somewhere. Now, what we could do now is we could say we are interested in an alpha level set, meaning we are only interested in those raster cells that have a membership value greater than a certain threshold. How could we do that? We could first determine the height of the final fuzzy set, because we want to normalize it. So we want to have values between 0 and 1. Currently, our values are not between 0 and 1. Our highest membership value here is it says here 0.5 something. So we would have to calculate the height of the fuzzy set. We can do that by using a raster statistics tool to find out what's the height of the fuzzy set. Then we could divide the final result by the height, which gives us a normalized fuzzy set. And then we could calculate, for example, an alpha level set, take 0.75 level. So with the raster layer statistics tool, we can find out the highest membership value, which is in this particular case, when you look at this, in this particular case, it's 0.96. would be the highest membership value. So we could take the raster calculator to normalize our result by dividing it by the height of this result, giving us a normalized version. And then we could take the alpha cut, or the point, in our case, the 0.75 cut, by looking at our normalized final result. And if the values are greater than or equal 0.75, we assign a value of 1. Otherwise, we assign a value of 0. And that gives us, as you can see here on the right-hand side, this result in a greenish color. These are all those raster cells that have a membership value of greater than 0.75. So I leave that for you to try it out yourself. You have the instructions, basically, how to do it in QGIS. For those of you who are using ArcMap, I have prepared a Python script here that would allow you to do the same thing using a Python script in ArcMap or in ArcGIS Pro. Of course, you could also do it with the model builder, and you could also do it, of course, in QGIS using models in QGIS. But I wanted to show you the step-by-step approach. So I will make this Python script available for you also, so you can try it out. It basically, for those of you who are familiar with Python programming in ArcMap or ArcGIS, it should be no major thing. Perhaps as the last thing, I could run it in ArcGIS Pro. This is the high elevation that we did at the beginning of the class. I will remove it. And what I'm going to do is I will use the Python window in ArcGIS Pro. I will load this code. Where is it? I will load this code. Just have to find it. This one. And then I can run this code. And if I didn't do anything wrong, after a few seconds, it should stop with a final result. Still working. It also will add all the intermediate results to the map. And while it is running, I just would like to tell you that right after this class, I will have to travel. So you will find the recording and the additional information perhaps only tomorrow on the website. So I will have no time to take care of this today. I will have to leave. Okay, it's almost done. Okay, it is done. I click away the Python window. What we have here is we have our final results. Just click away the intermediate results. For aspect, elevation, and so on, distance, raster, slope, and so forth. Okay, now what we have in the end, we had a result that was the result after overlaying everything. That looks like this. So you can see here are the parks, military installation, they are all excluded, and there are the water bodies. Then what I did, I computed a normalization of this result, which looks exactly the same because the values are just spread between 0 and 1. And then I computed the 0.75 value level set, alpha level set. Yeah. I have to click away the topographic map and fill shade so that you can see. And what remains after this alpha level set are just these gray areas that you can see here. Only these grid cells have a membership value greater than 0.75. You see here one close to a lake. They are all near a lake, and there's nothing near a major road. Okay, so that is basically what I